Okay, so in this lesson right here, we're going to be looking at derivatives part 3, implicit and inverse derivatives. So more techniques on taking derivatives. So let's talk about the implicit rule. This is a technique for finding the derivative when it's not possible or it's not convenient to solve for y. So it's not in function form. Okay, and it's all mixed up. It's difficult to separate it all out. So let's look at some examples of what I'm referring to and how this works. Okay, so we're going to take this right here. We're going to find the derivative of x squared plus y squared equals 25. So we can see from this that it's kind of challenging to solve. This is not a function. To solve this for y, it would be challenging to do that. Okay, so the technique for implicit differentiation is that we're actually going to take the derivative of every single term with respect to x. Using our chain rule process, that makes that possible. So if I look at just this term right here, what is the derivative of x squared with respect to x? Well, that is 2x, lower the power by 1, times dx dx. Plus, now I'm going to look at just this term. What is the derivative of y squared with respect to x? Well, that is 2 times y times the derivative of y with respect to x, because y is now that inside function, equals, and the derivative of a constant is 0. That is implicit differentiation. Once we have this, we can now solve for dy dx if possible. Just a bit. Let's try it here. So we can solve this here. This is just a 1, so you subtract the 2x over here, and then divide by that 2, right? The 2y, and we end up with dy dx equals a negative x over y. And so that's how I can find the derivative of y with respect to x. And so my derivative now is going to be dependent on 2 variables, x and y, and that's fine. Okay. What about this one right here? This one can be written as a function of x. I can solve this for y equals, but do I need to? Sometimes if you don't need to, there's no point, no reason to do it. So let's take a look at this one. Same process, implicit differentiation. We take a derivative of each piece as we move along. The derivative of 2x with respect to x, 2 times dx dx. The derivative of this with respect to y is 2, and then times the derivative of y with respect to x. And then this is still 0. So as I make this a 1, subtract the 2, divide by 2, you end up with dy dx equals negative 1. So you don't have to solve something for y and then take the derivative. You can just take the derivative implicitly. And so here's some more examples we're going to do. I'm going to show you different things as we move along. So here we go. Let's take the derivative of this. This is your 2x times the derivative of x with respect to x. This should be plus 3y squared dy dx and 0. And then solving for the dy dx here, subtract that, divide by that, gives me that dy dx is going to be equal to a negative 2x divided by 3y squared. Okay. This one over here is a little bit more challenging. You want to be careful of this. Okay, this example is in here just to point this out to you, to how to do this one properly. The key to this one and the thing you got to watch out for is this term right there. 2 things are going on in here. The first one is that is the product rule. So you're going to have to do the product rule right here because this is the product of 2 different functions. And then there's also, to add more to it, there's a minus sign involved. So my recommendation is to do it how I'm going to lay it out for you so you can see that you can avoid any kind of sign issues that occur. First things first, this one right here is going to give me the 12x to the 3 dx minus. Now, because this is a product rule, I'm going to do this in parentheses. I recommend highly that every time you do the product rule or any of those specialty rules, that you always use parentheses to set it apart. The product rule is the first times the derivative of the second plus the second times the derivative of the first. And it's because there's more than one term in here. That's why, one other reason why I needed the parentheses here, because that's a minus sign. We'll have to distribute the negative sign throughout in a moment. This right here will be 3y squared dy dx equals 0 because the derivative constant is 0. This is our derivative. Your job now is to combine terms, move things around, and solve for dy dx. And notice we have two terms with a dy dx in it. So as we do this and clean all this up, we're going to get minus x dy dx minus y plus 3y squared dy dx equals 0. So the terms that don't have as dy dx move over. Terms that are left, you're going to factor out dy dx. So you're literally going to have now dy dx times 3y squared minus x equals y minus 12x to the third. So what does dy dx equal? All this divided by this. Okay? So that's how I can use implicit differentiation for that. So it takes some getting used to it, take your time, make sure you follow the rules, use the parentheses to separate things out as you need. Okay? I have a couple more examples we're going to walk you through. Let's do this one right here. So we're going to take the derivative of this side right here with respect to x. This is the natural log of y. It is 1 over y times the derivative of the inside function, which is y, which is dy dx. This is going to be 2x dx dx minus 3 dx dx. And then we can clean all this up and solve for dy. So dy dx equals, to move this to the other side, I have to multiply both sides by y. So we get a y times 2x minus 3. Okay? But what is y? Sometimes you can leave it like this, but sometimes you can't. What is y, though? Okay? Well, there is no exact y up here, but I can change this log equation to an exponential form. Remember the box, circle, triangle stuff we talked about in previous classes? That means this up here, if the natural log of y is this, then y must be equal to e to the x squared minus 3x. And if y equals that, then I can substitute this into this equation right here. And so the final answer, dy dx, can be written as e to the x squared minus 3x times 2x minus 3. Okay? And if you look at this, if I had changed the form to this already, okay, solved for y, and then took the derivative, you'll see that the derivative of this is itself, and then times the derivative of the exponent, because that's the chain rule, and the derivative of 2x minus 3x, 2x squared minus 3, excuse me, x squared minus 3x is that quantity right there. So this just shows you that you can do it either way. Here's another example with a trig function involved. What is the derivative of this quantity right here? The derivative of cosine is minus the sine. Same function, inside function, sine of y, chain rule, times the derivative of the inside function, dy dx, equals 3 dx dx plus 3 dy dx. And so we have 2 dy dx's and one that's not. So start moving things around. You can move it however you want. What I did is I moved this dy over here, made it positive, and then moved that over here, made it negative. So I end up with a negative 3 equals 3 plus the sine of y dy dx, and then I factored out dy dx. So dy dx is equal to a negative 3 divided by 3 plus the sine y. Okay, so there's a bunch of examples there to look at. I do have another one we're going to look at right now, a little bit different twist on things. Okay, so that was just implicit differentiation there. Let's look at this example right here. If the tangent of if this is the equation I have, then the value of dy dx at y equals negative pi over 4 is what? So I'm going to show you some techniques for this, some things to do. Okay, and so the first thing I want to do is start over here. Since I'm looking for a dy dx value, I need to find the derivative of this to find a dy dx. So I'm going to use implicit differentiation. So what is the derivative of the tangent? The derivative of the tangent is secant squared. So this becomes the secant squared of y, chain rule, times dy dx, plus 3x squared dx dx, plus the derivative of 9 is 0. Derivative of 0 is 0. And so now I want to solve this for dy dx. So moving things around, dy dx is equal to a negative 3x squared divided by the secant squared of y. And that's fine, but what we're going to end up having to do is evaluating, okay? And so I don't really, secant, is there a way I can I can leave it? It's not a problem. If I can plug in, numbers and get a value here and you're good with that. Or I can use the identity for 1 over secant, and I can rewrite this using the trig identity and get a negative 3x squared times the cosine squared of y, because 1 over secant is the cosine. So that is another way I can do this. This is using trig identities to get to this. Okay? So in my problem here, I'm going to need, so to evaluate dy dx when y is a negative pi over 4, okay, that's fine there, but I don't have an x value. How do I plug in here? How do I do that? So I need to find this value. When you're looking to find a value for x, from an equation, you have to go back to the original. So I want to find the x value, okay, when y is a negative pi over 4, which means I'm going to take y is a negative pi over 4 and plug it into the original equation and then solve for x. Plus x to the third plus 9 equals 0. Negative pi over 4 is a 45-degree angle in quadrant 4, and the tangent there is a negative 1. Please make sure you know your unit circle. So take the cube root of both sides, so that x is equal to the cube root of negative 8, which is negative 2. So now I have the x value. So here's how you would write evaluating with derivatives. The dy dx evaluated at the point negative 2, negative pi over 4 equals, and then once you write it this way, so this line right here means evaluate at x and y, because it's a point value. We have 2 variables here. If I only have 1 variable, then I would only have 1 number down here. Because I have 2 variables, I have the x and the y variable here. And now you just plug it in. Negative 3, negative 2 squared, This is the cosine of a negative pi over 4, and that's itself is squared. Okay, so when you work all that out, you're going to get, negative 12. Cosine of a negative pi over 4 is the square root of 2 over 2, and I'm squaring that. Work this all out, and you'll get the number 6, negative 6. So that's how that works. So a couple things there. Keep in mind, remember, if you're looking for a point or you need to find an x or a y, given one of them, you use the original equation. This line means to evaluate. This down here means what you're going to plug in for, since there's two of them here, the x and the y. Right? Here's another example that uses implicit. Let me back out just a bit. There we go. Which of the following is true about the curve, and there's the curve, at the point 2, 1? Okay? So, the derivative exists at 2, 1, but there is no tangent line at that point. dy dx exists, and the tangent line is horizontal. dy dx exists, and the tangent line is neither horizontal nor vertical. And dy dx does not exist, the tangent line is vertical. So that's what we have going on, and we have to figure this out. So since all of these are talking about dy dx, okay, let's go ahead and find dy dx. Now, before we do that, though, one of these stands out as totally ridiculous. Okay? Take a moment, pause it, see if you can figure out which one of these choices here makes absolutely no sense whatsoever. So hopefully you did, and you thought about it, you paused it. So the one that makes absolutely no sense here is A. dy dx exists at that point, but there is no tangent line at that point. But that's the definition of this. dy dx is indeed the slope of a tangent line at that point. That's what it is. So to say that this exists, but there is no tangent line, is telling you that, it doesn't make any sense. So A is already out of our picture here. So when you read these things, kind of look for things that don't make sense, and you can eliminate some answer choices right off the bat. So to do this problem, you got to start off with and find the derivative. So I'll write it down here, x squared minus xy plus y squared equals 3. Again, we have that product rule in the middle there, so be careful with it. I'm going to go, here we go, 2x dx dx minus the first times the derivative of the second plus the second times the derivative of the first. 2y, chain rule, 0. So I now have 2x minus x dy dx minus y plus 2y dy dx equals 0. And so dy dx is y minus 2x over negative x plus 2y. So there is our derivative. We're going to evaluate this derivative at the point 2, 1 and see what we get. So as I do this and I plug this thing in here, I'm going to get 1 minus 2 times 2, and this is a negative 2, 2 times 1. And what I notice here is what? The top's this, the bottom's this, right? And this is undefined. So what does that tell me? Since it's undefined, this derivative does not exist. Okay? So if the derivative does not exist, the tangent line must be vertical. Okay? And you can confirm that with the graph of this. And so our correct answer here is dy dx does not exist. You have a vertical tangent at 2 points. Okay? All right, let's do that. There you go. So I'm going to move this paper over so you can pause pause it and write the notes out full and complete with all my little side notes. So here's that first one. I have some side notes in there. So pause it right now. Okay. And then I'm going to move it up here. Pause it there. All right. So let's take a look at some other things that are here. This is the type of question that you would see like on an AP exam right here. Verify that for this relation right here, this is the derivative. And they will give you this and they will give you the derivative, and they're looking for your process in between. Okay? So literally they want you to find dy dx. So let's go ahead and do it. So starting with this right here, the derivative of y with respect to x. This is a natural log, and that's the u stuff. So it's going to be 1 over that times the derivative of that. That's 3 dx dx plus 4 dy dx. So what they want to see once you've done, they want to see have you done the derivative correctly. And the next thing they want you to do is they want you to do whatever you need to do to get dy dx involved. So I have this fraction right here. This is on the bottom. And I can try and distribute it. It gets very cumbersome right there, but you can actually get rid of the fraction in a problem, remember, by multiplying by the least common denominator. So in this case, I'm going to multiply both sides of this equation by that quantity, which means I'm going to have 3x plus 4y times a dy dx equals a 3 plus a 4 dy dx. So this has a dy, these have dy dx's. I'm going to move that over there. And I now currently have, and factor out the dy dx, I'm going to have dy dx times 3x plus 4y minus the 4 I just brought over. And that's equal to 3. So solving for dy dx by dividing that quantity, I'm going to get 3 over 3x plus 4y minus 4. Confirming what they said it was. So on the AP exam, when you see this question like this is what they're looking for. They're watching your process. Okay? So there's that. That is implicit. It is one of your major techniques. Here's the problem again I just did. Now we're going to look at the differentiation of inverse functions. Okay? So, little recap here. If I have two functions, f and g, that are inverses, okay, they will be inverses if ab, which is on f of x, and ba would be on the inverse of that, g of x. They are symmetric about the line y equals x. Okay, remember the inverse is you're switching the x and the y's. So that's why this way, see, this was an x, that was a y, now that's x and that's y. You switch the x with the y. Okay? If f of x and g of x are inverses, the table values, you're just switching the x and the y values. That's what's going on. I hope you remember this. Two functions are inverses if and only if. So by composition, okay, this is your verification. If I give you two functions, you can verify if they are inverses or not. If I know this composition is equal to this composition, which is equal to x. If that occurs, I know the two functions are inverses. Here is an example. If f of x is x to the third plus 1, and g of x is the cube root of x minus 1, are they inverse functions? And you show the composition for both cases, and notice how they're both equal to x. So that's how you can do verification with composition. That's really very quick inverse review. Okay, so let's look at how we're going to use this. So let's take a look. Here's an equation, y equals x to the third. I want you to find the slope of the line tangent at x equals 2. Okay, so as soon as you see I'm asking you to find the slope, that means it is a derivative at 2. So you start off by finding the derivative of this with respect to x. So dy dx is 3x squared dx dx, which is just 1. I want to find the derivative. The slope of the tangent is the derivative evaluated when x equals 2, which means simply to plug in 2. And this is how you should write it, just like this, and then you get the answer 12. Okay? And if you did a quick sketch of this thing, x to the third, it's going to look something like this and do something like that. So in that 2, you're literally right about here, because if I plug in 2, I'm going to get 8. And so the slope of that line right there, you can see is fairly steep at 12. Okay? So following the same concept here, then we're going to do the same thing here. Here's this function. I want you to find the slope of the line tangent at 8. Okay? So, same thing. What is g prime of x? So first thing you want to do is you want to make sure you see this as x to the 1/3. Then I'm going to get 1/3 x, lower the power by 1, dx dx. So then what is g prime at 8? This is how you would do it in function form. This is how you do it in dy dx form. This is how you evaluate in function form. So we have this right here. We're going to plug it in, and we get 1/3 times 8 to the negative 2/3. This is just going to get flipped over. It's going to be this basically 1/4, and I get 1/12. Okay? And again, if you looked at the graph of this thing, it's going to look something like this. Remember. And then where is 8? 8 is way out here, and that's the slope we're looking for there. 1/12. Well, that's kind of interesting, isn't it? When I did this one, which is at the point 2,8, it was 12. When I did the inverse of it at 8,2, I now have 1/12. So they are kind of looks like they're going to be related in that fashion. Okay? So let's go take a look at it. So this is g of x. What is the derivative of the inverse of g at e squared? Okay? So let's go over here and take a look. So what I did over here first is you can make a table of values. We're going to do that real quick. And here is x, and here is g of x. Okay? And then over here, we're going to have another table of values, which is going to be x, and then it's going to be the inverse. Because remember, they switch order, don't they? Okay? So let's take a look at this. Here's my function g. Right? Since I have to take the derivative of g inverse, let's find the derivative of this, the inverse of this, excuse me. So this here is a y value, that is an x over here, and for inverses, we switch the x with the y. So the inverse now relation is going to be x equals e to the 3y. Okay? This is the inverse relation. By switching the x and y, you're now in the inverse realm. We want to find the derivative. Okay? So we're going to take this thing right here. We're going to solve this out, try and solve it for y so I can take the derivative of it. So this right here is going to be the natural log of x equals 3y. y, take the natural log of both sides, okay? And then we're going to solve for y. I get y equals 1/3 the natural log of x. And this is g inverse. Because it is a function, I can now claim it as an inverse function of g. So that is what I just did. I did not do a derivative. I'm finding an inverse. I found g inverse of x. Now I can take its derivative. Okay? So what is the derivative of this? So what would be g inverse, I use what, square brackets, prime of x? It's 1/3. And the derivative of what natural log of x is 1/x. Okay? Now, what we have to do here is we have to start figuring out the numbers in here. Okay? So up here it was 2882, right? So over here we have this thing right there. Okay? And so how do I find these numbers? We want to plug in this into this. Okay? So what does the x have to equal to get? So what does the x down here have to get so that I can get e squared up here? Okay, so that's what we're trying to accomplish. And to do that, you're simply going to put e to the 3x equals e squared. I got to find that x that produces this. Okay, so by doing that, I can then solve this out using our solving rules. And I know that x has to be 2/3. So what this means is when x is 2/3, g of x is going to be e squared. Right? Plug in 2/3, e squared. Which means, because this is the inverse, if I invert this, e squared is going to be 2/3. Okay? I just invert it because they're inverses. So that means now I can come over here and figure out, make sure you can see what I'm doing, the derivative at e squared, and that's going to give me 1/3 e squared. And that is my answer. Okay? So let me take a moment here. I'm going to move it over and show you the original notes. And then some stuff underneath it. So there's the original, what I did, show you a little graph action going on. Here's the one I just did right here. You can zoom in and kind of see it. Okay? Pause there for a minute for you to write. Here we go. I'm going to move up. These examples show the relationship between the slopes at the companion points on inverses. It seems that if f of x and g of x are inverses, and if f of a equals b, and further, if f prime at a equals m, then g prime of b is 1/m. Okay, think that through. If they're inverses, we know that this is true by definition. So taking the derivative, think about it. So taking the derivative of this with respect to x, because by chain rule and stuff, produces this right here. Solving for this, remember g is now the inverse. Solving for g prime will produce this. That's why there was that fraction involved. The issue here I have with this formula here, as long as you have it in your mind straight that g is the inverse of f, then this is a lot cleaner. For me, sometimes I want to keep it straight in my head. I will change the g stuff to actually represent the inverse function of f. So this is written as the derivative of f inverse of x. That's this, because g is the inverse of f. equals 1 over f prime, and then g is the inverse of f. Okay? So this is the alternate form that I use. You want to know this. You want to have it memorized. It's going to be on your test. Let's look at an example. I'm going to move it over so I can write on this. Let f be a differentiable function such that f of 5 is 20, f of 7 is 5, f prime of 5 is this, f prime of 7 is that. The function g is differentiable, and g is the inverse of f. So g is f inverse for all x. What is g prime at 5? Okay? So first things first, put your data in a table. You need to make your tables. Okay? I need a table that represents the f function and then the inverse f function. So from what I know, if this is x and this is f of x, from what they gave me two values. When x is 5, f of x is 20. When x is 7, f of x is 5. So based off of that, remember g of x is the inverse. Remember, this is f inverse. So all I have to do is flip these over. Okay? By formula, g prime of x equals 1 over f prime of g of x. That's the formula right there. Then it's just a matter of plugging in. So what is g prime at 5? You're just going to plug 5 in here. It's 1 over f prime of g of 5. Okay? Which means it's what? It's 1 over f prime, g at 5 is 7, which is 1 over, I forgot, g prime at 7 is a negative 5 over 2. And so then I end up with the answer, flipping this over, negative 2 bits. There you go. Let's look at another one. H is given by this equation right here. H of 1 is 2. If h inverse of x is the inverse of h, what is the value of this? H inverse, the derivative of h inverse at 2. So same process again. Okay? I start by making a table. So they told me when x is 1, h is 2. That's what they told me right there. Okay? Then I have my formula. Using this formula right here, which is the same as that. That's why I memorized it this way. I know h inverse prime of x is going to be 1 over h prime of the inverse of x. That's my formula. This tells me I have to find the derivative of h. So normally what I do in a problem like this is I take and make my table, and then I also take my derivative. All right, so if this is this table, then I flip it for the alternate, for the inverse table. This will be 2, 1. So I have that down now. You're going to see why I do that. And then I want to find h prime. These are the three things that I do every single time in a problem like this. So h prime is going to be 5x to the 4th plus 3. And so once I have these things, I should be ready to go. So what is H inverse prime at 2? It is 1 over H prime at H inverse at 2. H prime at H inverse at 2 is 1. So I need to find H prime at 1. Okay, so what is H prime at 1? It's basically going to be 5, 1 to the 4th plus 3, or 8. So that is 8. So that is 1 over 8. And we're done. That's how I do this problem. I write my formula down. I put in my table, or try and find my first table with the H, and then I invert it for the inverse. If I don't have it, then I find the derivative. Then I start plugging stuff in, finding what I need, plug that in to the derivative because that's what I needed. I got 8, and then you're done. It's pretty much, that's the process you follow for this technique. So that concludes this video. There's a lot in there. We'll talk more in class.